When the Artemis 1 mission launched on November 16th, some people expected that the path that it took in the sky would lead directly to the moon, and that's where it would stop. They noticed that it seemed to miss the moon from their perspective, and they think it should have looked something more like this. This misconception is not exclusive to space deniers, though. In fact, one of the spectators next to my telescope as I tracked the launch can be heard remarking that it went past the moon, evidently against their expectations.
That thing passed the moon. That thing passed the moon. That thing passed the moon.
Indeed, here is a stacked streak shot from Reds Rhetoric's GoPro footage, filmed from the same spot where we both tracked and filmed the launch, and as you can see, it doesn't hit the moon. So, what's the deal? Here's a 3D representation of its initial trajectory and parking orbit. This is from flightclub.io, the same site Reds used to successfully, predictively track the launch of the rocket. Artemis 1 goes into a low Earth parking orbit, before performing the Translunar injection burn almost one orbit after launch. It was just after the Translunar injection, or TLI burn, that I caught this clip of Artemis 1 rising into sunlight one orbit after launch, from the very same site that I had just filmed the launch from. One day later, I tracked the Orion capsule once again, this time using my telescope and deep space camera to take a series of 30-second exposures that were aligned based on the orbit of Orion. Stacking those exposures revealed that Orion was exactly where it should be, and I was able to use the coordinates over this session to then calculate the orbit of Orion, combining it with the observation I conducted one orbit after launch. I used the programs LFind and SatFit by Scott Campbell to find an initial TLE-based solution, and I used the eccentricity of this solution to then constrain FindOrb and come up with this solution with geocentric orbital elements that I could then plug into other programs like Orbiter Spaceflight Simulator. We can use Orbiter to simulate the launch of an SLS rocket at the time that the launch actually occurred and see if we can hit this target orbit. Furthermore, we can also use Orbiter to simulate the flight the rest of the way to the moon, and see if the amount of fuel available in the European Space Agency's service module was enough to deliver the Orion capsule to the close approach that it experienced a few days later. Here's Orbiter 2016. I've inserted an Orion capsule at the target orbit and propagated it backwards to before launch. Just as a reminder, this orbit represents the orbit it had after the TLI burn. But we're going to try to fly to the parking orbit first. To do this, I'm going to use a generic SLS Block 1 mod that uses the multi-stage MFD, and I'm going to target an orbit with an inclination equal to the post-TLI orbit that I measured. Everything else about the launch guidance of this mod is totally stock and left alone, and this mod is several years old at this point, but hopefully it'll be good enough that we can get into a parking orbit that allows us to reach our target post-TLI orbit. Here we go, let's find out what happens. The rocket now conducts its roll program to get on the correct heading and start pitching down to build up horizontal velocity to reach that parking orbit. As you can see, the remaining burn time is several minutes long, so I'm going to go ahead and time accelerate this part of the recording to get us to the parking orbit faster. There go the SRBs, and here comes the launch abort system jettison. Notice the green line is getting ever closer to the yellow line. The green line denotes the current orbital plane of SLS as it launches, and the yellow line denotes the orbital plane of our target orbit. Now on the left is an orbit diagram with Earth as a gray circle, and the SLS trajectory is a green ellipse. That empty circle up at the top of the ellipse represents the apogee point, or point farthest from Earth. As the burn continues, that ellipse grows, and eventually it will be entirely outside the gray circle, but the perigee point, or point closest to Earth, will still be inside Earth's atmosphere so that the core stage can be disposed of. The ICPS and Orion will perform a perigee raise maneuver a little bit after launch so that it doesn't fall back into the atmosphere. Now the engines have shut off, and in reality that would be the end of the core stage's performance. But I'm going to reorient the spacecraft here and do a little bit of cleanup with a small burn to actually reduce the apogee a bit, because in reality SLS didn't seem to reach quite such a high apogee in the parking orbit as far as I can tell. In reality, you couldn't relight the engines like this, but in orbiter you can, and I'm just going to do this to bring it a little bit closer to what SLS really did in reality. Since I was using the default guidance options from a mod that are several years old, it's not going to perfectly match reality, so I'm just correcting for it here manually to get it a little bit closer in line with what the real parking orbit was like. I'm going to brighten things up here for a moment so you can see first stage separation from the ICPS. The ICPS is the upper stage known as the interim cryogenic propulsion stage. I quickly exited and resumed the simulation. This saves your progress, and I wanted to do this to avoid any issues that might happen if I should have a crash to desktop, which I did experience a few times in practice runs, and I didn't want to lose my progress on this full run of the whole launch through the lunar flyby. I'm now starting to set up the MFD on the left to target the target orbit and be able to perform the TLI burn. Just as a reminder, the whole point of the simulation is not to set up the TLI burn to hit the moon based on where I think the moon will be in the simulation. The point is to match the orbit that I measured of Orion as closely as possible, and hope that from there I can reach the moon. Alright, I've now set up the parameters of the burn on the MFD on the left. DTE 5,300 seconds is the time to the burn. Truly, that's the time to the middle of the burn, and because the burn is 18 minutes long, we need to start the burn a few minutes before that countdown hits 0. dV just below it, or delta V, is how much we need to change our velocity in order to match the target orbit, about 2,600 meters per second. That's how much we need to accelerate our current velocity in order to match that orbit, and it's going to take almost all our fuel to do it. But first we're going to spend a little bit of that fuel to raise our perigee point so that we don't fall back into the atmosphere as the SLS core stage will. We're going to do this at the apogee point, and it won't take very much fuel to do it. Right now our perigee point, or PEA, is 37,000 meters or 37 kilometers above the surface. That's well inside the atmosphere and enough to pull us out of orbit, so we need to raise that to about 200 kilometers just to be safe. A quick external view here, you can see the SLS core stage slowly falling behind us, and the ICPS and Orion leading the pack. We're now going to time accelerate to the apogee point, and then burn our engine in the prograde direction in order to raise the perigee. The apogee point we're aiming for is this little hollow circle on the ellipse of our orbit. I'm now raising the throttle to full power and raising our perigee point. You can see the PEA number increasing, and we're using the ICPS engine, and we're going to burn a little bit of that fuel that we're ultimately going to use to perform the TLI burn. But again, it's not going to take very much to push us past 200 kilometers perigee. So there we have it. We've raised the perigee point successfully. We can now proceed to the point where we're going to perform the TLI burn, which is about 3,280 seconds away. And again, we're going to leave a little time at the beginning before that countdown reaches 0 to actually start the burn. We're going to start it when that countdown hits about 535 seconds. In my testing before this run, it seemed like that was a good number to get us close to having an overlapping orbit with the target orbit. Right now it's showing a hypothetical orbit of what it will take to reach that target orbit, but I'm going to disengage the hypothetical orbit when we start the burn and watch the real orbit grow until it overlaps with yellow target orbit. Now, the relative inclination difference between my orbit and the target orbit is about 0.19 degrees. It's not too bad, and we will clean that up after we do the TLI burn. Now, in previous runs, I had not actually tried cleaning up the initial core stage burn to make it more realistic to the true parking orbit. And what I'm going to find out is, spoiler alert, 535 seconds is a little too short, actually. I should have added a few seconds to that, and I'm going to have to clean that up after the TLI burn. But nevertheless, that's where we're going to start, at DTE 535. Here we go. I apply full throttle and start the burn. Now I'm going to hit HTO to turn off the hypothetical orbit and watch the true orbit slowly raise until it overlaps as much as possible with the yellow target orbit. This process is going to take about 18 minutes, so I'm going to time accelerate both in the sim and here in the video to try to get us to that end point as quickly as possible. Okay, that's the end of the TLI burn. I'm now going to check how well our plane is aligned with the target. So there's the descending node. We're going to do some cleanup when we reach that point and take out the last of the relative inclination at 0.19 degrees. It won't take very much fuel, and we have a little bit of fuel left over, about 21 seconds of burn time left on this stage. I'm going to temporarily brighten this external night view, and you can see Florida down here. Now, in reality, the SLS and ICPS were already over Florida at this time, so we're a couple minutes behind where we should be, but we are in roughly the correct orbit, and we're going to do final cleanup on that so that we match those orbital elements that we were aiming for as much as possible later on. Now, the reason we're running a couple minutes late on our orbit is because, again, the apogee point of the initial parking orbit was a little bit higher than what it should have been. In reality, it was a little bit lower, so the Orion and ICPS went around the Earth faster. Orbital mechanics is a bit counterintuitive. The higher you go, the slower you go. The lower you go, the faster you go. But as we come up here, we can see that we are on the right trajectory. We're going from west to east over Florida. And as we come up over Florida, we'll start to see that the sun is beginning to crest the horizon, just as it did when I saw it pop into sunlight as it flew back over the launch pad, one orbit after launch. Now I'm going to do a small burn to take out that relative inclination by burning in the positive direction at the descending node and reducing the relative inclination to 0. And there we go, we hit 0 degrees relative inclination to our target orbit, exactly as we wanted, but we can still see that the green line of our orbit and the yellow line of the target orbit don't perfectly overlap. Again, that was due to starting the TLI burn a few seconds late. So I'm going to burn sideways and clean that up and get those orbits to perfectly overlap, so that our orbital elements match the target orbit as much as possible. Okay, this is the attitude I need to burn in, so I'm going to throttle up. This shouldn't affect our relative inclination, nor should it burn us in a prograde or retrograde direction. We're burning at 90 degrees to those directions. And there we go, you can see that the green line is now overlapping the yellow line more and more, and as soon as it hits pretty much perfect overlap, I'm going to throttle down there all the way, and we now have matching orbits. So now on the orbit display on the right, I bring up the target orbit so that we can compare the orbital elements to our orbit. So we can see excellent agreement between these orbits. For example, the inclination is, of course, as we know, directly on 30.54 in both cases with 0 degrees relative inclination. Eccentricity of our orbit, ECC, is 0.9707 versus the target, 0.9700, very close. The LAN, or longitude of ascending node, is 10.42 for our orbit. It's 10.41 for the target orbit. So I'm now going to reorient the spacecraft and detach the Orion capsule from the ICPS upper stage. So there we go. Those are now separated, and Orion is flying free. Pop out the solar wings there. Now, this mod doesn't simulate the articulation of those solar panels, of course, nor does it have the cameras on the tips of those panels, but it's just a little static display there to show the solar panels. That separation event imparted a little bit of velocity to the Orion capsule and caused our orbit to start to diverge a little bit from the target orbit, which is not desirable. So I'm going to turn the spacecraft around here and burn us in the opposite direction to restore us back to the target orbit. So I'm going to apply a little bit of throttle back in the direction of the ICPS, and we can see that the green ellipse of our orbit is now once again starting to overlap with the yellow target orbit. And there we go. So once again, if we take a look here, the inclination is still exactly on, 30.54 in both cases. The eccentricity of our orbit is now 0.9706 versus the target of 0.9700. Our apogee point is 446.4 million meters versus the target of 446.1 million meters. Our perigee is a little bit lower at 375 kilometers versus the target of 520 kilometers, but still pretty close. Again, our longitude of ascending node is about 10.42 degrees versus the target of 10.41, so extremely close there. Our argument of perigee is 21.11 versus the target of 21.08. Again, very close. We're running just a little bit behind where we should be in our orbit compared to the target orbit, 0.46 degrees for the mean anomaly versus about 0.54. And similarly with mean longitude, we're at 31.98 versus the target of 32.04, but it's still not far behind. So what we've achieved here is we've hit the target orbit that I measured from my own observations of Orion and the ICPS. And we can now see if this allows us to get to the moon. I'm now going to time accelerate to the point in time where I observed Orion the next day from Florida with my telescope, and I'm going to verify whether it would have been visible from Florida at that time. If you look at the map on the left, there are some yellow plus signs. One of those is our spacecraft, and a green shape surrounds it. That large green shape that surrounds North America designates what part of the world can see our spacecraft at the present time. Now at 10:53 Universal Time, this was the time where I observed the Orion spacecraft from Florida, and we can see the green shape now forms a much larger shape over the world, and Florida is included in that shape. So you can see the gray and black areas denoting daylight from darkness, but the green shape also covers Florida beyond where the gray shape ends. That indicates that Florida's in darkness, as it was starting to become twilight, but I could still see the Orion spacecraft about 20 degrees above the horizon. Now, a few hours after I finished my observation of Orion with my telescope, Orion performed its first trajectory correction maneuver at about 14:32 Universal Time. This put it on course for the close flyby of the Moon that carried it about 81 miles, or about 130 kilometers from the lunar surface. So we're now going to time accelerate to the point in time where the trajectory correction maneuver occurred, and we're going to do our own trajectory correction maneuver to see if we can put ourselves on course for the Moon with the amount of fuel that Orion had available. We're now at the point in time where the trajectory correction maneuver happened. We're facing in the retrograde direction, so we're going to burn the engines full and start to drop that DT min value in the window on the right to reach a value of about 86.3. That should bring us very close to the lunar surface. Okay, it doesn't take very long. I actually overcooked it a little bit, so I'm going to use the translation thrusters and take some of that back out and get us closer to that 86.3 value. We'll leave it around 86.25. That should get us very close indeed. As we can see from the bar designated main prop up in the top left corner, it's still mostly full, so it didn't take much of Orion's fuel to put us on course for the Moon. That indicates that the orbit that I measured for Orion shows that it really was on course for the Moon, and it didn't take very much fuel to get it to reach a very close approach to the Moon, as we will see shortly. We can see the Moon growing quite large, so let's now look at our orbit and see how close we're really going to get to the Moon. We see a PEA, or periloon distance, of about 50 kilometers, which is even closer than Orion actually flew by the Moon. I'm actually going to reorient the spacecraft and take some of that out so that we get closer to the true value of about 130 kilometers. I'm just going to use the small attitude control thrusters to put in some translation thrust or side-to-side motion in order to increase that PEA and get it up to about 130 kilometers, or at least a little bit closer to it. Alright, that should do pretty good actually, because PEA is still slowly increasing over time. You can see it just ticked up to 120.7. That's because the Moon's gravity is not the only effect on our orbit right now. You can see G at the bottom of the screen is 0.71. That indicates that other sources of gravity like the Earth and Sun are influencing our orbit by about 30%. As we get closer and closer to the Moon, you'll see that G value increases towards 1 as the Moon starts to dominate more and more of our orbit. When we reach periloon, we'll actually do a burn here and see if we can put ourselves into something of a distant retrograde orbit, which is what Artemis 1 was targeting. In truth, it took a couple burns to get to that orbit. They did a single burn during the lunar flyby, and then they did another burn a couple days later to put it into a DRO, or distant retrograde orbit. For the purposes of our simulation, though, we'll end it at that point and just take a look at the Earth going behind the Moon and then Earth rising out the other side just after the lunar flyby. Now you might recognize some of the topographic features here of the moon and the lighting conditions. This is very similar to what we saw from Orion during the actual mission, because of course we're essentially recreating that trajectory ourselves based on my own observations of Orion from before the first trajectory correction maneuver. We arrived at the moon a couple hours early, but in general the approach trajectory is still very similar. I'm just going to time accelerate here until we get to Earth's setting over the limb of the moon. Just a beautiful shot there of Earth going behind the moon as seen from Orion. Now of course the orientation of the camera and of the Orion spacecraft doesn't necessarily match historic reality. I'm just hand flying it here till we get to Paraloon, and then we'll do that final burn to put us into a distant retrograde orbit. A few more exterior shots here of the lunar surface as Orion approaches Paraloon, just about 125 kilometers above the surface of the moon in this case. Now, the historic burn that occurred here was about 2 minutes 30 seconds long, so we're going to burn for about 2.5 minutes and verify, of course, that we still have plenty of fuel left over after that burn, because of course Orion's mission isn't done at this point, and we just want to make sure that after everything we've done, Orion does have what it takes to do this mission. I will spare you with some time acceleration here, but if you pay attention to the time up in the top right, kind of behind my logo, you can see that we actually do burn for about 2.5 minutes. And that's it. We can see that even after this 2.5 minute burn, Orion has plenty of fuel, and we are in a sort of distant retrograde orbit. Of course, not the real orbit that Orion went for. We just tried to do it in one burn here, not trying to recreate the exact flight path of Orion at this point, but just demonstrating that after intercepting the moon and doing this close flyby, Orion did have the fuel that it takes to do this mission. I'm extremely happy with this result. I was able to track the Orion spacecraft with my own observations, feed that into Orbiter, and actually use that as a target to fly to from the launch pad with SLS, and then fly from that target orbit out to the moon for a close lunar flyby, just as the real Artemis 1 mission did. We didn't have to rely on NASA data to do this. We did it ourselves with our own observations and our own simulation. Before we go, we'll take a look at Earthrise, which will be against the darkened lunar limb, as that part of the moon was not receiving sunlight, and just as NASA showed during the outbound flyby, Earthrise does indeed occur over that darkened limb. Thank you so much for watching, and until next time, clear skies, folks.